In this video, which will be our last video of the Unit 2.1 topic, we're going to have a look at the idea of atom economy. So this section begins on page 29 of your booklet. So atom economy is a measure of how efficiently the atoms in the reactants are used in a chemical reaction. It's essentially a measure of the percentage of atoms which are converted into useful products, the products that we actually want out of a reaction, as opposed to some side products as well. Quite often the side products are not useful and are in fact wasted. So here is an expression, an equation for calculating the percentage atom economy. There are different ways of expressing this calculation because in fact the total mass of atoms in the products will equal the total mass of atoms in the reactants. So it doesn't really matter which way you calculate it, but here's one way that I suggest you use and just stick with so that you're using the same one each time. So the percentage atom economy is the mass of the atoms in the desired product divided by the total mass of atoms in all of the products times by 100%. It is important that you also realise that this percentage atom economy will be for a given reaction. That given reaction will have a balance symbol equation, and so therefore you must take into consideration the balancing number ratio. So if there is a 2 in front of the formula that is your desired product, then you multiply the mass of the atoms by 2. This is not what we normally do when we're thinking about things like reacting mass calculations and so on, but we must take that into consideration with our atom economy, and we'll see that in our examples. So let's have a look at worked example 1, and it would be helpful to have a periodic table out in front of you so that you can get your relative atomic mass information. So worked example 1 involves the addition of bromine to cyclohexene, a reaction that you probably won't be familiar with, but that doesn't stop us being able to calculate the atom economy. And this is what we call an addition reaction, which means essentially 2 molecules are adding together to make 1 molecule. So cyclohexene and bromine are adding together and they're forming what we call dibromocyclohexane. Again, that sounds very complicated. Don't worry too much about what these molecules actually are. And what we'll see is that by their very nature, these addition reactions are very atom economical because there's only one product. But let's see that actually in the maths. Let's let the numbers prove it. So you'll see that I've set these worked examples out with a table. You don't have to draw a table every time you do these calculations, but you may find it helpful. So what I would normally do, first of all, is to list my useful products, calculate the RFM of them, and then list all of the products and calculate the RFM of those. So our useful product in this instance is dibromocyclohexane. So I've just written the formula of it there. And you'll see that there's no balancing numbers in front of it. So it's essentially 1 times by this. If there was a 2 balancing number, then I would have to multiply the RFM by 2. So here it's just a case of calculating the RFM of this molecule. So that's going to be 6 times by 12 for your carbon, 10 times 1 for your hydrogen, and adding on 2 times 80 for your bromine. Just make sure you do these calculations carefully because obviously if you get the RFM wrong, then your value of atom economy is going to be wrong. So if you put that into your calculator, you will get an RFM of 242. So that's the RFM of your useful product. There are no other useful products, so we can just put a dash there, and your total is 242. Then we need to work out the RFM of all of our products, and in this case, that is only our 1 molecule. So that is our useful product, but it's also just one of the products. And we've just worked out its RFM as 242. And if there were any other products, we would list them here and work out their RFM. But there are not. There are no other products in this reaction. So again, your total is 242. So what is my percentage atom economy? Well, if you look at the expression above, percentage atom economy is the mass of atoms in the desired product. So that's our first column here. We work that out to be 242. Divided by the total mass of atoms in the products. Again, that's 242 because I don't have any other products, times by 100%. So obviously 242 divided by 242 is going to be 1 times by 100%. That's obviously going to be 100%. So this reaction obviously is very atom economical, because all of our reactants are being converted into useful products. We don't have any products that are wasteful. Let's have a look then at worked example 2 in the next page. In worked example 2, we see the reaction between bromobutane and sodium ethoxide. Again, not a reaction you're probably familiar with, but the balance symbol equation has been given to you, and so we have all we need. So this reaction produces butene, it produces ethanol, and it produces sodium bromide. And we're told here that butene, C4H8, is our useful product. So butene is our useful product. You will always be told in the question what the useful product is. It may not be given to you in those words, but it may be, you maybe were told in the question, this reaction takes place to produce butene, and you know therefore that that's your useful product. That's the one that we're wanting to make. So we want to fill out our table with our useful products and then all of our products, thinking back to our expression of atom economy being the mass of the atoms in the useful product divided by the total mass of the atoms in all of the products. So our useful product, as we said, was C4H8. And we can see from our balance symbol equation that there's just one of those. So I only need to work out the RFM of one of those formulas. So the RFM of butane is going to be 4 times 12 for your carbon plus 8 times 1 for your hydrogen. If you put that into your calculator, it should work out as 56. There are no other useful products, so we can just put a dash here. Your total RFM then of your useful products are 56. Then the RFM of all the products. So here I would list your formulas first of all, remembering to include your balance symbol numbers if there are any. You can see that there are not any in this particular example. So one of our products is our useful products. Make sure you don't forget about that one within your list of all the products. We also have ethanol, C2H5OH, and we also have sodium bromide, NaBr. So what we need to do is calculate the RFM of all of these products, and we only have one of each of these in this reaction. You might want to pause the video and give it a go of calculating your RFM yourself. So for our butane C4H8, we know that that is 56. We've just worked that out. For ethanol, it's 2 times 12 for your carbon, plus 6 times 1 for your hydrogen, and plus 16 for your oxygen. So that gives us 46. And then for your sodium bromide, you've got 23 plus 80, and that gives you 103. So what we want to do now is to add up the RFM of all our products to get us the total RFM of all products. Put that into your calculator and you get 205. Now we want to work out our percentage atom economy, so we need to think about our expression for that value. So percentage atom economy is equal to the mass of atoms in the desired product divided by the total mass of atoms in all of the products times by 100%. So that's going to be our 56 divided by 205 times by 100%. Put that into your calculator and it should come out as a value of 27.3%. We normally do it to either one decimal place or 3 significant figures, but do remember that your value for percentage atom economy should always be 100% or less. It should never be above 100%, and it's only 100% if we had, like in worked example 1, an addition reaction where there's only one product, but other than that it'll be less than 100%. So if you get a value coming out as higher than 100%, you've done something wrong. So let's look at one last example, worked example 3. So we're told in worked example 3, this is a reaction you looked at in your GCSE chemistry. It says, in the blast furnace, carbon monoxide is used to reduce iron oxide to iron. And this is what I'm talking about. Sometimes you're not told in the question what the useful product is, in terms of it doesn't blatantly say the useful product is iron, but you're told here that we're using carbon monoxide to reduce iron oxide to iron, and therefore that's our useful product. So sometimes you need to look out for that in a reaction. So you may want to pause the video and give this a go yourself and then check the video for the correct answer. So if you want to pause the video now and try that. But let's have a wee look then at the useful products. So we've just said that our useful product is iron, but notice how in our balance symbol equation, we have 2 molecules of iron being produced. So we need to take that into consideration in our atom economy calculation. So it's going to be 2 times by my iron. That will be 2 times by 56. Which is 112. So just be careful. This is not what we normally do, like in our reacting mass calculations or limiting reactant calculations where we're bringing the number of moles across. We normally just use that ratio when we're moving number of moles across. And so this seems kind of counterintuitive, but what we're totaling up is the total RFM of my useful products and then the total RFM of all the products. And because we're forming 2 molecules of iron in this particular reaction, then I've got to take that number into account. So please try not to mix that up with then your moles calculation. But here we need to take that into consideration. So there's no other useful products. And so the total RFM of my useful products is 112. Then we want to fill in our column for the RFM of all the products. Don't forget about your useful product there as well, because that's all the products. So we're going to have 2 times our iron and 3 times by our carbon dioxide. Again, taking into consideration our balancing number. So we know that the total RFM of 2 iron atoms is 112. And then for our carbon dioxide, if we get the RFM of 1, first of all, and then multiply it by 3, so we're doing 12 plus 2 times 16, which is equal to 44. But then we need to do 3 times by that, which gives us 132. We then want to total up our RFM of all our products, so that's 112 plus 132, and that gives us 244. Percentage atom economy then is equal to your mass of atoms in the desired products divided by the total mass of atoms in all of the products multiplied by 100%. So that's going to be our 112 over 244 times by 100%. Put that into your calculator and it should come out as 45.9%. Over on page 31 then you just have a bit of information to help you understand atom economy and why it's used by chemists. So we talked before this section about the idea of percentage yield, and that is useful in determining the efficiency of a chemical reaction in terms of converting reactants into products. It's important for profit, but it doesn't take into consideration the waste products and how much waste we are producing. But chemistry, like all other industries, is concerned about its effect on the environment, particularly when it comes to waste. And so what we might have is a reaction that has a high percentage yield, but has a low atom economy. And that might be good for profit, but it's not good environmentally or in terms of what we call green chemistry. In other words, chemistry that is concerned about the effect on the environment. So this means that the other products in the reaction will be waste, and with a high percentage yield, if we have a high percentage yield, then there's just more of them because you're producing or you're converting more of your reactants into products. So what chemists want to do now is look at reactions that have a high percentage yield but also a high atom economy to reduce waste. So if you were asked in an exam, what is the importance of atom economy? Well, it's really driving reactions that will have a high atom economy to reduce waste. It's all about reducing the waste. So we want to come up with reactions that have a low percentage of waste products. And that's actually one of the main drives of green chemistry. So it's important that you know the reason why we use atom economy and also the expression for atom economy. Sometimes in your exam, that's all you're asked for, and that's back on page 29 that we've been looking at and we've been using for our calculations. But sometimes you're just asked for the expression, and that's really it. So all that's left for you to do now to complete this unit is to complete exercise 9, which is some questions on atom economy. So if you complete exercise 9, questions 1, 2 and 3 you'll probably want to do on file paper. But question 4 onwards you can do in your booklet because they are just screenshots of exam questions, and so you can do them directly on your booklet. The answers are in teams, as I've done with other exercises in this topic. So if you mark your work using the answers on teams and get in touch if there's any answers that you're getting that are not matching, and let me know if you can't get the correct answers or need any help. And then if you submit your marked work to the assignment on Teams by the end of this week, if possible. If it runs into next week, that is okay, but I just really encourage you to get this wrapped up and finished this week, because what that means is this topic is complete, and then from here on in we can focus completely on our revision for the first assessment. So if it's not in at the end of the week, that's okay. Certainly we'll want it completed for after Easter, but I think it would be best if you finished it this week and had that off your mind. So as always, please get in touch if you have any questions, and I hope you get on okay with these.